Hello, in the past few videos we discussed what is C, time complexity and smallest prime factor, largest prime factor, etc. Now let's discuss the next concept of number 3. So the next one is GCD. So what is GCD? It is greatest common divisor. It should be the greatest one of both divisors which are common. For example, GCD of 4 and 8 is 4 because it is the highest number which is divisible by both. Similarly, of GCD of 10 and 15 is 5. So how to find this? In C++ there is a direct method underscore underscore GCD which gives the GCD of A and B in log n. But what if we want to type the code and get GCD of given numbers? So the idea is the GCD can never exceed the maximum of both. So we can start from maximum number and we can reach till 1 because GCD of 2 and 3 is 1. So the least GCD possible is 1. So we can traverse till 1 and we are checking whether it is divisible by both A and B. If it is divisible by both, it is the maximum number. So it is GCD. So we are returning J. But time complexity is of n, which is not very good because we got a log n one by default. So we should be getting off log n or less than that in our approach. So it is wrong. Coming to next one, let's assume that GCD of A and B is k. So as GCD is k, A can be written of k into x, B is equal to k into y. Because GCD of 10 and 15 is 5, 10 can be written as 5 into 2 and 15 can be written as 5 into 3. So it can be written as GCD into some other multiple of that number. So it is k into x and k into y. And now what is a minus b? It is k into x minus y. So if you observe what is the GCD of b and a minus b, it is also k because we have k in the both. So GCD of a minus b comma b is also k. So similarly, what if we are trying to find a minus 2b? Similarly, the GCD of a minus 2b comma b is also k because we can here the extra factor of 2 will be there, but the GCD is k of both. So if we do these until GCD of a comma a by b into b comma b, so it is the division. For example, 14 by 3 is 4. So if we do until this, the GCD of both will still be k according to the same idea. So how can we write this in the simplified form? GCD of a comma a minus b into b. So it is simply a mod b because it is the remainder and a minus quotient into b is the remainder itself. So it can be written as GCD of a mod b comma b is equal to k. So from this we assume that k is equal to a is equal to kx, b is equal to ky. We found that GCD of a comma b is equal to GCD of a minus b comma k, a minus b comma b, and so on till GCD of a mod b comma b. So GCD of xy is equal to GCD of yx. So we can just simply simplify this as GCD of b comma a mod b. So this is also equal to k. So we reduced a comma b to a simplified one. But how it is useful? So let's discuss time complexity. So what is a mod b? It can be surely less than or equal to b minus 1 because we are doing modulus with b. It can never exceed or greater than or equal to b. So if we assume that b is greater than a by 2, if b is greater than a by 2, we assume that a minus b initially so that we are able to perform a minus b and a minus 2b and so on. So if we assume that b is greater than a by 2 and as already a is greater than b, what can be the value of a mod b? It is a minus a by b into b. It is just the definition of modulus. So from this, a greater than b. So surely a by b is greater than 1. So it is greater than 1. So it is surely less than a minus b because it is already surely greater than 1. So we have minus n here. So it is surely less than a minus b. And we assumed that b is greater than a by 2. So this is still less than a by 2. So if b is greater than a by 2, a mod p can surely be less than a by 2. And what if b is less than a by 2? Then a mod b is equal to a by 2 minus 1 because it is surely less than or equal to b minus 1. And now b is still less than a by 2. So it will surely be less than or equal to a by 2 minus 1. So regardless of a comma b, a mod b is surely less than a by 2 as we discussed in the both cases. So but what is the use here? So we are able to simplify GCD of a comma b to GCD of b comma a mod b. So this is equal to GCD of A mod B comma B as well. So in in one operation, we are able to convert A into A by 2, because let's assume this as A by 2, the maximum value that A mod B can be. So in one operation, we are able to do it in, we are able to half the value. So how many iterations are required to get GCD? So GCD of 0 comma any number is the number itself. For example, GCD of 6 comma 0 is 6, because 0 is regardless here and other number is GCD. Similarly, GCD of any number comma 1 is also 1. So the base case is if we find 1. So initially the number is A. So GCD of A comma B, we approximately change it to GCD of A by 2 comma B, and next GCD of A by 4 comma B, and so on till GCD of 0 or 1. So surely the time complexity is log n, because we are able to reduce the number by 2 in every iteration. So in this way, by recursion, because GCD of A comma B is equal to GCD of B comma A mod B, and the base case is, as we have discussed, if B is equal to 0, then return the A, because if we have 0, the GCDs are the number itself. So if the B is 0, then return A. It's the final GCD. So with time complexity of log n, we are able to achieve the GCD of given numbers. But what is the use of GCD? Let's check other example. So ax plus by is equal to c. We have given a and b, and c. We have to find whether x comma y solution exists. That means whether there exist solutions which have both are integers. So both x and y should be integers. So we have to return yes if there exists a pair x comma y which are integers, and we have to return no if there are no pairs. So how can we do this? Let's take a small example. If the first one is 3x plus 6y is equal to 9. So 1 comma 1 is a very straightforward solution. So yes, we found a solution and we get it in 1 comma 1. And if the second example is 2x plus 4y is equal to 11. So what is this? 2x is always even and 4x is always even. So can even plus even be odd ever? No. So there is no solution, and we can return -1 or no solution as well. So how can we do this, or how can we use GCD? Let's assume that GCD of A comma B is K. So as we discussed, A is as GCD of AB is K, we can write A as K into X and B as K into Y. As we have X and Y variables already, we assume that A is equal to K into P and B is equal to K into Q. So we can write the given equation as K into Px plus Qy is equal to C. So we are sure that we have a multiple K here. So we have solution only if C mod K is equal to 0, because we have K here. So we are sure that to exist a solution, C also can be written as K into some other number R. So the solution exists only if C mod K is equal to 0, else it is not possible. In the first example, GCD of 3 and 6 is 3 and 9 mod 3 is equal to 0. So the solution existed, and one such example is 1 comma 1. And coming to second one, GCD of 2 comma 4 is 2, but it is not divisible by 11. So we are sure that solution does not exist. So we are able to solve half the part, whether the solution exists or not. But how to find whether, but how to return the solution, any one solution. So let's come to this part. And now coming to the other idea, ax plus by is equal to c. So what is the minimum value of c such that the solution exists? It is surely GCD, because it should be a multiple of GCD, and the least multiple of GCD is the number itself. So if we are able to find the solution of GCD, can we find the solution for C? Yes, because for example, if we are able to find the solutions of this as x0, y0, can we find the solution for C? It can be simply written as C by GCD into x0, C by GCD into x0, because we can just multiply by C by k on both sides and we can get the solution for given idea as well. So now the main part reduces to find the solution of ax plus by is equal to k, because we are sure that the solution exists, and the main idea is to return the pair which satisfies the given condition. So now let's assume the initial equation as 1. As we have discussed in the recursion, GCD of A comma B is equal to GCD of B comma A mod B. So what if we are using a function, other function, and doing the recursion and already updating x comma y as well? So a comma b is modified to b comma a mod b. So the new solution according to it is x1 y1. The initial solution is this, and the values that are satisfied here are x and y. So similarly, GCD is simplified into b and a mod b. So now the solutions let's assume as x1 and y1. So b into x1 plus a mod b into y1 is equal to k, and a mod b is equal to a minus a by b into b, which is the definition of mod. And what if we try to simplify it? We can take a into a1 y1 outside and b common from this term and this term as well. So we are left with this a into y1 plus b into x1 minus a by b1 is equal to k. So if we observe equations 1 and 2 carefully, we see that x is equal to y1 and y is equal to x1 minus a by b into y1. So from basic recursion of GCD, we are able to update the solutions as well. But the base case of GCD is if b is equal to 0, return a. But now what is the base case for x and y? So now the base case is that we are finding solution for ax plus by is equal to k. And now we want the solution xy when b is equal to 0 and k is equal to GCD, right? So GCD of a comma b, a comma 0, because b is equal to 0 in the base case. So now GCD in the base case is GCD of a comma 0, which is a. So now we want the solution for ax plus by is equal to a, because in the base case GCD is a. So b is 0 as per the base case again. So we just want the solution for ax is equal to a. So what is the solution for it? It is just the x is equal to 1 and y can be any, because we found that b is equal to 0 in the base case. So regardless of y, x should be 1 and y can be any. So the base case here is if the b is equal to 0, x is equal to 1, y is equal to 0, return a, because the GCD is a, and we are assuming x1 y1 and getting the GCD by using recursion. And after the values getting from this, how can we update here? So these both are this x is equal to y1 and x1 minus y1 into a by b. So we are updating x and y based on the recursion of the next state. So and finally we are getting the answer, which is GCD. So from the simple function we are able to get the GCD and the pair which is satisfying. So let's check the code. It is similarly exactly before. If we are just to find the GCD, no need of parameter section y, and the base case is if b is equal to the return a, else return GCD of b comma a mod b. But now if we want x and y, initially we can call the function, the second function. We can pass these both by reference because we want the solution for the next one, and based on the next one, we are updating the solutions for the present one. So x1 comma y1, and we are calling recursion GCD of b comma a mod b comma x1 y1, and x is equal to y1 as we have seen here, x is equal to y1 and y is equal to this, and finally returning the values. So for example, the values are 115. We got that GCD is equal to 5, and one solution is x is equal to minus 1 and y is equal to 7. So 100 into minus 1 plus 715 is equal to 5. So the solution satisfied. If you have any doubts, post in the comment below, drop a like. See you in the next video.